AstroTour tonight. Our speaker here, Christa, is going to tell us all about how our solar system came to be and how it may not have always been the same, which I find very interesting because nothing much seems to change in my lifetime. All right. So Christa is a postdoc here at the Canadian Center for Theoretical Astrophysics and so she's a total expert on this. She did her undergraduate study at the University of British Columbia, then moved on to Arizona, where she did her Ph.D. And now she's here. Something interesting about Christa that I learned today is that she has a dog and a cat, and her cat's name is Kilo. You know how many kilograms? So that was pretty cool and nerdy.
I'm geeky like that. I roll with the geeky.
Awesome. So I'll leave the geekiness up to Christa. Welcome.
All right, where did my pointer go? There it is. As Jiley said, I'm going to be talking to you about the planets. This talk is inspired by my husband. And there he is talking to the dog. What happened was he and I were having a conversation, and I will often rant about what my science is and say, oh, you know, I learned something new today, and so on and so forth. So this one time I was having this good rant, and I went so on and so forth, and all of these things, and you know, Neptune migrated, and it had this effect, and he went, whoa. Roll back to the part where Neptune migrated. What do you mean Neptune migrated? Neptune's always been where it is, right? Well, no. And so hence this talk. All right. So I'm going to spend a second, and you'll see another holy jargon Batman later in the talk. So one piece of jargon I will use because I'm entrained in it and I just can't seem to avoid it is the AU. So the AU is the current distance between the Earth and the Sun, or rather the average distance between the Earth and the Sun over a full year. So this sets the scale for all things in the solar system. And so when I talk about all of these distances, I'm going to be talking about them in terms of AU. So just remember, 1 AU is where Earth is now. I figure since I'm going to be talking about where the planets were, I should first start off with where the planets are. Helpful, I know. So near the sun, there's the big sun there, and right beside it over here are the terrestrial or rocky planets. We've got Mercury, Venus, Earth, and Mars. Further out, we have the giant planets, Jupiter, Saturn, Uranus, and Neptune. And for scale here, remember Earth is at 1 AU, so that little green ball is at 1 AU. Jupiter is at 5, and Neptune is at 30 AU currently. And you can see that there's quite a range in sizes in the planets. Jupiter is gigantic, and Earth and Venus are kind of piddly, and then Mars and Mercury are just downright dinky. Call them as they are. In between the terrestrial planets and the giant planets is this region known as the asteroid belt. So all of these little white dots here between the orbit of Mars on the inside and Jupiter on the outside are called asteroids. These asteroids are small. So remember when I just called Mars dinky? These things are really tiny. Ceres is the largest asteroid, and it has the bulk of the mass in the asteroid belt, but it is still quite small. The asteroid belt has structure. So here this is a plot of, oh, I forgot to change over that jargon. So this jargon means distance. So distance from the sun here on the bottom, and the number of asteroids here on the y-axis. So this is the number of asteroids as a function of distance. And you can see that there are these gaps. And these are called the Kirkwood gaps. What's going on here is that Jupiter is interacting with the asteroids. So let's say you've got Jupiter and an asteroid. And let's say that that asteroid has exactly half the orbital period that Jupiter does. So Jupiter goes around the sun every 12 years. This asteroid goes around every 6. So let's say they start off right here, and they move forward and forward and forward and forward. And so the asteroid has made one full orbit around the sun, and Jupiter's only made it halfway around. They keep going, and they end up exactly back where they were. This sets up a situation where the asteroid will get kicked by Jupiter in a repeated way. It's like pushing somebody on a swing set. If you push them at the same point in their swing, then you'll build up how high they get. But if you push them at random points, then you'll just end up with somebody very annoyed on a swing set, and they won't be swinging very much at all. So this is like you're pushing the asteroid with a very consistent timing. And so that makes these asteroids get all very upset, and they go unstable, they go away. So that's more or less what creates that structure. Out beyond Neptune, there's another region of small stuff called the Kuiper Belt, and Pluto is the shining example here. Pluto was discovered in the 1930s. The next Kuiper Belt object was discovered in the 1990s, but now we know a whole bunch of them. And so here, if you've got the giant planets, Jupiter, Saturn, Uranus, and Neptune, these blue and white dots out here, beyond Neptune's orbit, these are the Kuiper Belt objects. These are also quite small. Down here is the Earth for scale. So there's a fair number of big ones, but again, they're really the debris of the solar system. They're very small. Lastly, way out there is the Oort cloud. The Oort cloud is something like 100,000 AU from the sun. These are very cold, and these things are only very barely bound to the sun. So they're orbiting the sun, but only kind of just because the sun happens to be around and nothing else really happens to be around. If another star came along, they desert us. But in any case, we've got this Oort cloud out here. All right, so that's more or less where the planets are now. Where were they? How did they get there? So in the beginning, dun, 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 we had a nebula. So a nebula is a fancy name for a whole big cloud of gas and dust. Mostly gas, a little bit of dust. And by dust, I mean like really your dust bunnies. Just some sort of solid stuff. The nebula, because it gets a little bit more massive for its own good, collapses. Hello? So then the nebula collapses, and when it collapses, it forms a disk, for reasons you can ask me about later. In the disk, the solid stuff will every once in a while collide with each other. And if the velocities are low enough relative to each other, they'll collide and stick. So if you take two little small things and you collide and stick them, and then you take two slightly bigger things and you collide and stick them, and then you take two slightly bigger things and you collide and stick them, eventually you can collide, stick, all the way up to the planets. That is the general idea. In addition, there's this thing called the snow line. So at the snow line, this is the distance from the sun at which it is cold enough so that all of the water can be in the ice phase. So everything can be in one of three phases. It could be gas, it can be liquid, or it can be solid. So this is the temperature in the original disk where it's cool enough for water to be ice. And that means that this water ice, this solid water, can participate in this collide and stick process and also help you build things. So it's no coincidence that outside of the snow line is where the bigger stuff is, because they have even additional material to build themselves up from. So you have rocky stuff inside the snow line and some rocky and icy stuff outside the snow line, and you get the planets. Huzzah! The solar system, my talk's done. Not quite. This is great, but it's not the whole story. There are some things in the solar system that are not explained by this very general, simple model. And the first problem is that Mars is small. So let's say that you've got this disk of small stuff, and you want it to undergo this collide stick until you get planets. And so what you want to end up with, here we've got distance from the sun and the mass or size of the thing. You've got Mercury, Venus, Earth are about the same size, and then Mars. So what you'd like to happen is for this collide stick process to just give you the planets. But that's not what happens. So this is the output from a numerical simulation, where basically what happened is you gave a computer a disk and you said, here, crunch some numbers for me until you can tell me what would happen a whole bunch of years in the future. So these boxes here are the real planets. So there's Mercury, Venus, Earth, and Mars. And Earth and Venus get reproduced fairly well. You do this whole collide stick thing and you get things that are about the right size. But you don't get things that are Mars-sized, not at the right distance. You create way too many things that are like Earth-Venus-sized. So if nothing else was going on and it was just this naive model that I told you a couple of minutes ago, then Mars should be something like the size of Earth. But it's not. It's small. How can you fix this? So if you say, all right, I've got this disk, but I'm going to remove all of the stuff that's outside 1AU. Remember, 1AU is where Earth is now. And I'm going to take this truncated disk and I'm going to let it undergo a collide stick process and see what we get. And this is the output from another simulation where they've cut off the disk at 1AU. And they do a pretty good job of getting close to what Mars actually is. So you have to truncate the disk to get Mars to be approximately the right size. All right, that's weird. There's another problem. The current mass of the asteroid belt is 4% that of Earth's moon. That's really small. It's too small. It's too small for the asteroid belt to have formed the size of stuff it has. If you take the planets and you smear out their mass over their orbital region and you add back in hydrogen and helium based on like what the sun has. So if you look at the sun and you say the sun's got so much iron and so much hydrogen, and then you look at the planets and you go, well, this planet has such and such amount of iron. So in the original disk, there must have also been such and such amount of hydrogen because the sun's got that much. Then you can build up what you think the original disk would have looked like. And there's a huge gap where Mars is and where the asteroid belt is. They are much, much less massive than they should be based on the amount of mass that the Earth has and the amount of mass that Jupiter has. If the plot doesn't make sense, just remember it just doesn't have very much mass. All right, the other thing about the asteroid belt is it's got some sort of substructure. So in the inner part of the asteroid belt, there's a whole bunch of these asteroids called S-type asteroids for a weird and convoluted and strange reason. But anyway, they're called S-type asteroids because, yeah. I can tell you about it later if you're interested, but yeah. And in the outer part of the belt, there's a whole bunch of asteroids called C-type asteroids. And the main difference between these asteroids is that the S-type asteroids inside are water poor, so they don't have very much ice in them particularly. And the C-type asteroids are water rich. If this formed where it is now, you'd expect some sort of nice continuum, where on the inside you have the dry stuff and on the outside you have the wet stuff, but you've got this very nice smooth transition between the two. So that somewhere in the middle you have something that's got like, that's like halfway in between. We don't see that here. What we see are the two different populations. You've got dry stuff and you've got wet stuff, and you don't have stuff that's of intermediate iciness. So these two populations, this suggests that one of them at least didn't form here, that it was put here later or that something happened, because these two populations forming on top of each other like they are is not something that would have happened. All right, now I'm going to tell you how we fix this. But warning, warning, this is an area of active research. There's a very significant chunk of the planetary science community which does not believe what I am just about to tell you. I know. I'm not sure I believe it, but it's a good working model. And as scientists, what we really need to do is we need to come up with models for other people to beat down. And when they beat them down, they can come up with why it was wrong and point us in a direction of a better model. So this is the current working model to solve the problems that I've just outlined. All right, so this involves just another little bit of background. So this is a computer simulation of a gas disk. You've got the sun in the middle, and this hole here in the middle is just because computers have a hard time resolving really, really small things. And the things in here orbit really, really fast, so it's hard to make a computer do that well. But in principle, the disk goes basically all the way in. And then out here, you've got a planet. And this disk would like to be smooth and kind of the same everywhere, but there's a planet in the middle of it, so it can't be. So this planet, A, carves a gap out of the disk, and B, there's the planet, it makes these spiral waves in the disk. And these spiral waves are places in the disk where the disk is more concentrated, so there's more mass where I've put these arrows. And so because mass attracts mass, it's gravity, it's the law, these streamers here, they tug on the planet. And because this one is just a little bit more massive, it's a geometry thing, mostly a geometry thing. But anyway, this one is a little bit more massive, and so the planet moves inward. So this one's got a slightly stronger tug, the planet moves inward. The situation is a little bit different if you've got two planets. If you've got two planets and their gaps overlap, then the spiral structure that the planets induce in the disk looks different. And if you work through all of the complicated its differentness, then you'd realize that these planets will move outwards. So how does that work for us? So if you've got, say, a whole bunch of small stuff here, and we're calling it the S-type water poor stuff. If this black dot is Jupiter, and this black dot is Saturn, and then out here we've got all of the icy, water-rich stuff. First, Jupiter and Saturn will move in, because they've opened their individual gaps, and because of these streamers, they will move in. But eventually, Saturn it's going a little bit faster. So Saturn will catch up with Jupiter, and their gaps will merge, and then they will move out. So in this process of Jupiter moving in and then moving out, and it's called the Grand Tack because there's some sort of analogy with sailboats, but I don't know anything about sailboats, so I don't really know what the analogy is, but apparently this whole changing direction thing is called tacking. There you are. Anyway, so all right, so you took Jupiter and Saturn, you moved them in, and then you moved them back out. And when you did that, Jupiter saw all of this small stuff here, and it threw it out here. And then when Jupiter and Saturn move back out, Saturn and Jupiter both see this disk of water-rich stuff and throw it in and throw back in some of the dry stuff. So you end up with an asteroid belt that has some dry, water-poor stuff and some wetter, water-rich stuff. Huzzah, we've solved a problem. And you truncate this inner disk at 1 AU, or approximately 1 AU. So you get a small Mars. So this is a good reason for that disk to be cut off at 1 AU. And you also end up with an asteroid belt that doesn't have as much mass. So there we are. That's the Grand Tack, and that's more or less the first major way that the planets moved. And that's really cool. I think it's really cool that Jupiter came in to like 1.5 AU and truncated the disk at 1 AU. Like that's really close to the sun. And that's really cool. Yay, science. But it doesn't explain everything. All right, so here we have distance from the sun and number of asteroids. So this is like the plot where I showed you the Kirkwood gaps, but the histograms are a little bit more coarse. And you can see the Kirkwood gaps, the disk, the gap here, the gap here, the gap here. So this is what the asteroid belt should look like. This is what the distribution of stuff at different distances should look like after the Grand Tack. But this is what we have. So this shaded histogram is the structure of the real asteroid belt. These are normalized so that the maximum number of asteroids in a given histogram bin is the same as it is in reality. But you can see that here, 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 and a little bit here, there are asteroids that should have been there, but aren't. There's missing asteroids. Another thing that's going on here is the Jupiter Trojans. So these white dots are the asteroid belt, and this blue circle is Jupiter's orbit. And this chunk of stuff and this chunk of stuff in Jupiter's orbit, orbiting with Jupiter, these are called the Jupiter Trojans. So these are things that if they were forming there when Jupiter was forming, they shouldn't have stuck around. They should have moved out of Jupiter's orbit when Jupiter did things like open a gap in the disk. So these shouldn't really be there. Another thing is called the lunar cataclysm. This is also called the late heavy bombardment, but lunar cataclysm sounds better. So the lunar cataclysm. So what happened here was that we had the Apollo missions, and they were fantastic. And they brought us back moon rocks. And what you can do with rocks is you can ask, when is the last time that this rock was molten? When did this rock last melt? And if you do that, you realize that a lot of the moon rocks were last molten at 3.9 billion years ago. And this is interesting because the moon was already pretty old by that point. The moon would have formed something around like 4.2, 4.3 billion years ago. So lots of things being molten at 3.9 billion years ago is kind of weird. So what happened? What we think happened is that the moon underwent a period of really heavy bombardment. So that if you pummel the moon with enough stuff, if there's lots of stuff in this inner solar system around where the moon is, and you pummel the moon all over with this stuff, then you can make all of these rocks temporarily go molten and then freeze again, so that when you date when they were last molten, you'll find that they'll all cluster around that impact age of about 3.9 billion years ago. So that's pretty interesting that at 3.9 billion years ago, when there shouldn't have been a lot of stuff around the inner solar system, planet formation should have cleared all of the, most of the small debris out already, that the moon was suddenly very heavily pummeled with a whole bunch of stuff. This is called the lunar cataclysm because it was a cataclysmic amount of bombardment or something along those lines. All right. Another problem is the resonant Kuiper Belt objects. And here we have the next holy jargon Batman. So I'm going to use this term eccentricity, and the eccentricity is how elliptical an orbit is. So if an orbit is a perfect circle, the eccentricity is 0. If the orbit is not quite a perfect circle, then the eccentricity is a little bit bigger than 0. And if it's really not a perfect circle, then you'll get eccentricities up to almost 1. So if you look at this plot, this is distance from the sun versus eccentricity. This is the Kuiper Belt. Remember that Neptune is here at 30 AU. So all of this stuff is the Kuiper Belt. It's out beyond Neptune. And there's some stuff that's at fairly low, pretty circular orbits. But there's all of this stuff highlighted in red, which appears on these vertical lines. So they're all at the same distance from the sun. The orbits are all the same size, but there's a varying amount of how elliptical these orbits are. And there's a lot of stuff in these resonant populations. These locations are exactly at resonances. So like in the asteroid belt, where you could imagine Jupiter going around every 12 years and an asteroid going around every 6 years, here Neptune's got an orbit of 160-ish years. And so at small integer ratios like 2 times that, 3/2 times that are where all of these resonances are. And there are a lot of things, there are a lot of things in these resonances. So if you just plunked the planets down where they are right now and just said the things that are resonant are the things that happen to be there, you would not get this abundance. All right, so now I'm going to tell you how to fix all of these things. I know that was a lot of problems, but we'll come back and review them. All right, so let's say that we started the giant planets off in a more compact configuration. So Jupiter is currently at 5.2 AU, but let's say it started just a little bit outside that. Neptune is currently at 30 AU, but what if we start it at more like 20 AU? And then these planets will move just a little bit, and I'll tell you how. So Neptune sees this primordial Kuiper Belt out here, this whole sea of small stuff. And when a Kuiper Belt object comes by Neptune, it gets its orbit changed a lot. But Neptune gets its orbit changed just a little bit. So if you imagine, so let's say you've got one of those big medicine balls that are really, really heavy, and you try to throw it. If you throw it this way, you get knocked back a little. The same sort of thing happens when you throw a tennis ball, but you get knocked back a very tiny amount. But if you can imagine throwing millions of tennis balls by you, eventually the effect will build up. So every time Neptune throws a Kuiper Belt object in, it moves out just a little bit. And the next time it throws a Kuiper Belt object in, it moves out just a little bit. So Neptune is very good at throwing these Kuiper Belt objects in, and then Uranus passes them in, and Saturn passes them in, and then Jupiter throws them out. So what ends up happening is you send Neptune, Uranus, and Saturn out, and Jupiter you send in just a little bit. Until eventually you get the configuration that you have now. And this almost works, but not quite. So this is what's called the Nice model, and it's named after the town Nice in France, where most of the authors were at the time, not just because it's a nice model. It is a nice model, but it is the Nice model. So in the Nice model, you start out with the compact goodness. You'd think I'd been drinking, but I haven't. You start off with a compact configuration of giant planets, and you end with our current configuration of giant planets. And you start with this slow migration, the gradually Neptune throwing things in. But then you hit an instability, and suddenly the planet's orbits become eccentric. And when they're eccentric, Neptune can reach a little farther into the Kuiper Belt. It sees more of the Kuiper Belt. And this means that suddenly you get very fast migration. And then eventually, you kind of run out of small stuff to throw around, so you get a little bit of slow migration afterwards. So I'm going to show you a movie of what this looks like. So you've got Jupiter in red, Saturn in orange, and the two ice giants, Uranus and Neptune, in blue and purple. And then out here is the primordial original Kuiper Belt that Neptune is going to eat at very slowly. And over the course of this movie, you'll see it just kind of, the planets wiggle around, wiggle around, wiggle around, and then they'll go unstable for a little bit, and everything will explode, and then they'll settle back down. Yes, it is working. All right, so Neptune's slowly throwing stuff in, and then boom. And if you've got a careful eye, you'll notice that Uranus and Neptune switched places. Uranus and Neptune are more or less interchangeable. They both have about the same size, about the same mass, about the same composition. And in this specific scenario, when the planets go through their instability, they happen to switch places. This is not something necessary in the NEAS model. You don't have to have Uranus and Neptune switch places, but it's kind of fun. But hey, you know, things can be fun. All right, so does this solve our problems? It does. So if this is the asteroid belt that we could have had, and this is the asteroid belt that we have, what happens if these resonances weren't always in the same spot? By which I mean if Jupiter wasn't always in the same spot, if Jupiter moved inwards a little bit, then these resonances would have swept through the asteroid belt. And if you let that happen, then these two histograms actually look kind of the same. So if you started with the open histogram and you had Jupiter migrate, then you do end up with this. And you probably noticed that there's this other dashed line over here called the Nu-6. And it is also a resonance, but it's a slightly more complicated type of resonance called a secular resonance. But it is responsible for sweeping through and taking away most of the stuff on the interior here. So we've fixed the asteroid belt, we think. You also get the Kuiper Belt objects. What happens here is that you start Neptune out on an orbit, and this dashed line here is where its resonance is, or where one of its representative resonances is. So as Neptune moves out, the resonance also moves out. And if you have a Kuiper Belt object here on this orange orbit, and it's in the way, then as the resonance goes past, the Kuiper Belt object will get caught in that resonance. And then as Neptune and the resonance continue to move out, this Kuiper Belt object will get dragged along with the resonance. And as it gets dragged along, it gets more eccentric. So that's why these resonant populations reach up to eccentricities as high as they do, is because Neptune was moving along, it swept up a whole bunch of Kuiper Belt objects in front of it, and as it continued to drag them along, it gave them eccentricity. So the NEAS model is awesome. It sculpts the asteroid belt. You release a whole bunch of stuff at the same time, which you can bombard the moon with. You also get Kuiper Belt objects swept up into resonances. And when these things are messy, Jupiter also picks up the Trojans. This is hard to show in a video, so I didn't show it. But trust me, Jupiter picks up its Trojans along the way. All right, that's the NEAS model, and it's awesome. It's very nice. But still, there are some things about our solar system that aren't quite explained. So this is a really, really active area of research. Lately, we've been discovering a whole bunch of planets that are orbiting other stars. These are called extrasolar planets. And most of these planets that we've been discovering are very, very close to their star. So Mercury orbits in, I've forgotten the exact figure, but a whole bunch of days, 80-something days, let's say? 88, thank you. I have it written down somewhere. So Mercury orbits in like 88 days. But planets in the Kepler-11 system, for example, orbit in several days, 8 days, 13 days. There are planets we know of that orbit in 3 days. There are actually also a couple of planets we know of that orbit in like 8 hours. So these are all planets which are ridiculously close to their stars. And we don't have any. Why? You might have also noticed when I was talking about how Mars is small, there's Mars over there on the right-hand side. Mercury is also kind of tiny. And the reason that all the computer models were getting a small Mercury correctly is that they artificially truncate the disk on the inside edge too. So in addition to having your disk truncated at 1 AU, you've also got your disk truncated at like 0.6 AU. And then all of the terrestrial planets form from this disk that's truncated on both sides. And there have been excuses for why that might be reasonable. But in the light of finding all of these extrasolar planets, which it looks like probably formed pretty close to their stars, all of these excuses for why there was no solid stuff interior to 0.6 AU don't really make sense anymore. So there's no really good reason for this disk to be truncated on the inside edge. Also, Mercury is just kind of weird. So Mercury has a really huge iron core. Mercury is mostly core. If we made the movie The Core on Mercury, you wouldn't have to go down nearly as far. The Core is a very bad movie, very bad science. Anyway, if you compare Mercury's core, the relative size of Mercury's core, to the size of cores of the other terrestrial planets, you realize that Mercury really is mostly core, whereas Venus, Earth, and even Mars have a fair amount of rocky mantle sitting on top of the core. That's odd. So how do you fix this? Now this, I forgot to add this slide in. This should also get a warning, very active area of research. This is actually a paper that just came out earlier this year. So anyway, so the idea is that, if you want to ask the question why we don't have any planets interior to Mercury, the answer is, well, maybe we did. And they're gone now. Because if you pack all of these planets really close together, then sometimes you pack them too close together. And so every time they come near each other, they talk to each other with gravity and they move each other around a little bit. And if you do that a whole bunch, then eventually you can get them to collide. And you can send them into each other, you can send them into the sun, you can grind them down to dust and blow all that dust away with radiation forces from the sun and maybe actually get rid of them. So if you start off with this very compact configuration and then you have them collide into each other and sometime later you end up with Mercury. And Mercury, having gone through all of these collisions, would probably have stripped off most of its rocky mantle. So that's awfully convenient. All right. So that's more or less what we think has happened to the solar system. What will happen in the future? Mercury, again, I'm going to pick on Mercury, might go unstable before our sun goes red giant. So it seems that many people, scientists included, are very attached to our solar system and imagine that, of course, our solar system is stable for the whole lifetime of our sun. Obviously, it should be, right? Wrong. It is not. So if you move Mercury forward, if you put down all of the giant planets and you say, here, computer, move these planets forward and have them talk to each other with gravity, and let's see what happens a few billion years from now. You'll find that sometimes in the future, here's time along the x-axis and eccentricity along the y-axis, sometimes Mercury's eccentricity grows really high. And when Mercury's eccentricity grows this high, it puts it on a collision course with particularly Venus. And after it has a close encounter with Venus, you can do pretty much anything to it. You can throw it out of the solar system, or more likely into the sun. So if you do a whole bunch of these simulations, and each different color on this plot is a different simulation where you've moved the current position of Mercury by 3 centimeters. So depending on exactly where Mercury is right now, you might lose it sometime in the future. And so this time scale here goes from now to 5 billion years from now, and we expect that our sun will turn red giant 4.5 or 5 billion years from now. So sometimes you lose Mercury as early as 1 billion years from now. Sometimes you don't lose it until 5 billion years from now, but a reasonable fraction of the time, Mercury goes bye-bye before our sun does. All right, so that brings me to my conclusions. And wow, I'm almost exactly on time. All right, so if you took away nothing else from this talk, please take away that the planets moved, and they moved a lot. And when the planets move, they move around all of the small debris. And it's really through looking at this small debris, and here you can kind of include Mercury and Mars as the small debris, if you really want to. Because when the planets move, they move around everything else around them, you can have clues into how they moved. And in the future, the planets may continue to move more, and in particular, Mercury might disappear into the sun before our sun dies. So that's it. Thank you for listening.
Thank you so much, Christa. That was a very enlightening talk and actually kind of motivating. I might actually go for my Sunday run this weekend, you know, motivated by the movement of the planets.
That's right. The planets are moving, so should we.
Exactly. That's a good message. So we have about 5 to 10 minutes for questions for Christa, the expert on planet migration. Let's start with you over there.
So you mentioned when you talked about near the end about how Mercury in the future could be unstable and get thrown into the sun or away, or maybe into Venus.
Mm-hmm.
I guess if in any scenario Mercury gets thrown away or into the sun and the like, how that would affect how that would kind of change how the gravity now because less bodies.
Right.
How would that affect Earth, or would it?
It would, but not a whole bunch. So the planets do jostle each other around a little bit. So with Mercury gone, the jostling would change a little bit, but it wouldn't change really significantly. Like it wouldn't mean that Earth suddenly was able to reach a range of eccentricities that it currently can't, or something like that. So it would change in detail, but it wouldn't change in like real effect.
So not enough to destabilize the entire system?
No.
But is there a chance of it kicked into Earth?
There is a small chance, yes, that it could get kicked into Earth. That would be uncomfortable.
What kind of chance are we talking about here?
A, very small, very small.
Okay.
And B, I think we have bigger things to worry about.
Let's go with you.
Yeah, I still don't understand why these extrasolar planets have these closely orbited planets. You explained why we don't have it. Why do they have it?
Right, because, so I said that we don't have any because in our system we packed them a little too close and they jostled each other and sent each other unstable. So what happens if you don't pack them quite so tightly. Then if you imagine some sort of a distribution where you pack some things more tightly than others, then the extrasolar planet systems that we see that still have these inner planets have just managed to retain them for longer. And that's mostly because you didn't pack them quite as tightly as they probably were in our system.
So I have seen a lot of diagrams of the Oort cloud and the Kuiper Belt. I've never thought about this. Why is there a gap between the two? Is there a gap between the two?
Between what sort?
The Oort cloud and the Kuiper Belt.
Right. So the full answer is there might not be so much of a gap. So the Oort cloud probably also formed mostly in the Nice model. So when Jupiter was throwing stuff like out of the system, like totally out, it didn't maybe quite go totally out, it maybe ended up in the Oort cloud. So the Kuiper Belt is partially built on stuff that was at that distance originally, and partially built on stuff that Neptune dragged there. And so maybe there's an end, there's some sort of a gap after the stuff that Neptune dragged there and the stuff that was there originally, between that and the stuff that like Jupiter really flung out that made the Oort cloud. But we don't really have the observations yet. As we keep discovering more and more and more Kuiper Belt objects, we keep discovering more that are on really large orbits. So it might be that there is like a little bit of a lull, but there's kind of a continuum between the Kuiper Belt and the Oort cloud. But
So why do we have two different terms?
right. It's useful to have arbitrary lines sometimes. So, okay. So let's do a thought experiment. Let's say that you've got a whole bunch of pencil crayons and you want to divide them up. You'll put some in the red category and some in the orange category, but really there's the continuum. There's some that there's a pencil crayon that's orange red. But if you want to talk about the colors in a useful manner, you still recognize a division between red and orange, even though you know that it's not a sharp division. So it's the same thing here, that the Kuiper Belt is, what we call the Kuiper Belt is really a different beast from the Oort cloud. Even though they're connected, it's useful to divide, to put a line between them, even though that line is kind of arbitrary.
You've had your hand up the whole time.
What will happen to like the other planets when the sun dies?
Right, so that's an interesting question and also an area of active research. So what happens when the sun dies is that it will blow up to very large size, and it will also lose mass. So as the sun gets bigger and bigger and bigger, it might get so big that it encompasses Venus's orbit and maybe even Earth's orbit. Certainly Earth on its current orbit would be much too close. It would be definitely very fried by this big sun. But also the sun loses mass. And so as the sun loses mass, it changes the orbital energies, and this moves the planets outwards. So it's currently up for debate whether Earth gets swallowed, Earth gets fried, or Earth moves out fast enough so that you don't get completely fried, but just mostly fried. In any case, Earth's not going to be a happy place to be, so we should find somewhere else to move in 5 billion years.
Yes.
In other solar systems, why do the Jupiter-like planets form near their sun?
Right, so,
Oh, by the way, can everybody hear the questions?
oh, sorry. All right.
Sorry, I should have thought of this earlier.
So the question was, why do, in other solar systems, do Jupiters form close to their suns? The answer is that's complicated. So there's really two kinds of planets that are close to their suns. We find smaller things, so like Neptune or smaller than Neptune sized things close to their stars. And these, we think, have a reasonable shot of forming where they are. We also find what are called hot Jupiters, and these are really Jupiter-scale planets, the really, really big ones, and we find them on like 3-day orbits. These things, the hot Jupiters, probably didn't form that close to their stars. They probably migrated there. And so it would be a much more violent migration than any of the planet migration that happened in our solar system, but the hot Jupiters probably migrated. And the other ones, it's a work in progress, but it looks like we can probably form up to about Neptune scale things about where we find them.
Great. And 3 more questions. Yes.
In the Grand Tack model, you said that Jupiter was probably dragged closer to the sun by the spirals, and then it suddenly got pushed out. Did you explain why it was pushed out?
Right, it's because Saturn gets close, and so the gap for, so the question was, so Jupiter moves in, and that's because of the spiral pattern and the mass in that spiral pattern tugging on Jupiter. And then it moves out again in the Grand Tack. Why does it move out? And the answer is that Jupiter's got a gap in the disk, and Saturn has a gap in the disk. And when Saturn gets close enough to Jupiter, their gaps merge. And this changes the spiral structure fairly dramatically. And it changes the balance of where things get tugged.
So then the outside spirals start tugging more?
Yeah, more or less. It's a little complicated and it depends on details, but it looks like if you'd have a Jupiter planet and a Saturn planet, it specifically needs that Saturn is a little bit less massive. But yeah, you will change the spiral pattern so that you get tugged outwards instead of inwards.
Great. And yes.
In the Grand Tack computer model, you said there was a gap where the computer couldn't run the simulation because it was moving fast.
Right.
Is it possible that what was going on there had some kind of variable that affected the outer part that the computer did run simulation?
Right. So the question is, in the Grand Tack, I showed these models where you have the inner part of the disk carved out because stuff there is going too fast for your computer to resolve it well, and for your simulations to run in a reasonable amount of time. And the question was, does the stuff that happens in there matter? Can it have an effect on the stuff outside? And the simple answer is yes, it can matter. And as we get better computers, I look forward to us figuring out how. It probably doesn't overall change what's going on, but it will certainly change the details.
Okay. And last question up the top.
You said that the NICE model doesn't have universal acceptance kind of thing. Is there an alternative that has the same kind of predictive accuracy?
Right. So the NICE, the question was, I said that some of these models don't have widespread acceptance. Are there other models? So the NICE model is actually reasonably well accepted. The idea that the planets hit some sort of instability and then migrated quickly is reasonably well constrained from what happened to the asteroid belt and what happened to the Kuiper Belt. It's an open question whether or not it happened at the right time to make the lunar cataclysm, but you can take that or leave that from the model. The Grand Tack and what I call the lost planets, those are much more controversial right now. The Grand Tack in particular, there's an alternate model called pebble accretion, which is basically that you start off with pebble-sized things, and then magic happens, and then you end up with Mars being small like it should. And it has to do with how pebbles interact with the gas disk and how properties of the gas disk make it easier for for pebbles to collect on some things versus other things based on their distance from the sun. So that one is also, I'd say it's about 50-50 on that one. So both are interesting working models.
Thank you so much, Christa, for that. Will you be around for a few?
I will be around. Okay. Don't worry. I also intend to look through the telescopes.
Oh, okay.
So
we have plenty of opportunity to talk to Christa for the remainder of the evening. What will be happening in the remainder of the evening is that there are some planetarium shows occurring. If you book for a planetarium show online, then you need to be at an allocated location in order to go to the planetarium. If you're for the 9:15 p.m. show, then you should go there straight away. The location meeting is, if you go straight through 2 sets of doors, you'll find some elevators that look like that. If you stand around there, somebody will be there to take you to the planetarium. In particular, Heidi over here. For the subsequent shows, please turn up about 5 minutes earlier. If you're not attending a planetarium show, please join us upstairs on the 14th. Go up to the 14th floor using those elevators, and then climb a set of stairs to the telescopes. There will be a bunch of graduate student astronomy students, as well as Christa, as it turns out, will be showing you telescopes and a beautiful view of Toronto from high up above. And then lastly, this event runs every single month, and so the next one will be on the 1st of October at 8 p.m. I hope that you will join us there. And one last thing. As you were coming in, we would have handed you a sheet of paper to get some feedback from you about how we're